Hi, I'm Tom Park, Director of Software Solutions at Berry Consultants. In this video, I'd like to introduce you to ADDPLAN's capabilities for designing patient enrichment Phase 3 trials. Now, a patient enrichment trial is not, unfortunately, one that makes patients richer. Rather, it's one where we can adjust the mix of patients being enrolled into the trial to maximize those that are showing most benefit from the treatment. Now, this adjustment creates some multiplicity issues for a Phase 3 trial where strong control of type 1 error is required and some uncertainty around the required trial size. ADDPLAN PE addresses those multiplicities and uncertainties in a way readily accepted by regulators. Let's take a look. So now we're going to look at ADDPLAN patient enrichment. So in ADDPLAN patient enrichment, we have a frequentist approach to enrichment designs, in contrast to the enrichment designs we have in FACS, which use a Bayesian approach and are principally intended for a sort of a Phase 2 setting. Here we're looking more at the Phase 3. The patient enrichment module in ADDPLAN is only available in ADDPLAN Classic. It wasn't ported to ADDPLAN Neo by ICON. We might port it one day, but it won't be soon. We've got more important stuff to do, I'm afraid. And in this video, we won't be giving a comprehensive guide to ADDPLAN patient enrichment, but we'll present an example based on one, or some examples based on one in the user guide. So this is intended for confirmatory trials and using p-values and frequentist statistics. The amount of enrichment is quite limited. There's not going to be many groups. We're typically looking at just 2 or 3. What ADDPLAN does behind the scenes for us is to use a closed testing procedure to ensure that the control of the family-wise error rate is ensured, so we achieve the desired alpha level. What we can do is specify how many analysis sets we can include in the testing, one set always being the overall population, the last of the sets, and we can specify between 2 and 4. So because of this, in this kind of design, we can't calculate the sample size or power, and this has to be estimated using simulation. When we go into this mode in ADDPLAN, it doesn't have a design feature, which is what is presented for you when you want to do a sample size power calculation. You could simply go straight to the simulation mode. As well as an option to select which groups go forward, the enrichment step, the design can also include group sequential stopping and sample size reassessment, as we'll see as this example progresses. So this is Berry Consultants' point of view, quite a nice example because it takes ICE-by-2 as its context. The setting for the example is to imagine that from the ICE-by-2 platform trial in neoadjuvant breast cancer, a drug has graduated from that Phase 2 screening study and is going to go forward to Phase 3. And let's imagine that from ICE-by-2, the signature, the one patient population in which the drug was shown to be most effective, was in HR negative and HR2 positive, but it also showed some promise in the overall HR2 negative population, so including the HR positives. So the prevalence of the HR negative and HR2 negative population is about 34%. And then the prevalence of HR2 negative, this is in the overall population of neoadjuvant breast cancer, is about 63%. So rescaling that, the prevalence of the HR negative within the HR2 negative population is at about 54%. And we're going to need those numbers to set up our simulation. The other numbers we're going to need are what is the expected PCR control rate, the PCR rate, the probability of complete remission on the control arm. Within the HR2 negative, HR negative population, it's about 34%, and within the HR2 negative and HR2 positive population, it's about 23%. When you combine those, weighting them with the prevalence, the relative prevalences of the two subpopulations, we get an overall rate within HR2 negative of about 0.3. If we assume a PCR rate on control of 0.3, the overall rate for HR2 negative, and we look at possible responses on a treatment of variously 0.4, 0.45, 0.5, 0.55, and do simple sample size calculations, looking for a power of 90% and an overall alpha of 0.025, but divided in a Bonferroni adjustment to take into account we're taking two looks, one at the overall population, one at the subpopulation. We get respectively required sample sizes of over 1,000, 500, nearly 300, and 190. So what we're going to do is say we suspect that those two larger sample sizes are probably too much for us, that they'd be too expensive to run the trials, probably take too long. So we're going to target a treatment rate of 0.5 and use a sample size of 300. So the design is going to be a confirmatory trial, initially all in the HER2 negative population, and we'll have an interim halfway through at 150 subjects. And at that point, we have the option to restrict the second half of the trial to only enroll the HR negative and HR2 negative. Alternatively, we carry on with the entire HR2 negative population. So that's our selection point. And the rule we're going to use is that we'll continue in all the HR2 negative population if the treatment effect in the whole population is within 0.1 of the treatment effect. We won't do early stopping. We're going to use p-value combination to combine the p-values from the two stages before and after the selection using the standard inverse normal method. And to control the overall family-wise error rate, we're going to use a Bonferroni correction on the intersection tests. And all this is going to be done for us by ADDPLAN. We have to do very little except select these options. So in a moment, I'm going to show you the software, but firstly, I'm just going to walk you through the screens that would be, the different tabs on the screen that we'll be looking at. So from this cut of the screenshot, you can see we're going to be looking at 5 different tabs: the procedures, the sequential design, if we're using group sequential, the parameters, which is how to simulate the scenarios, the selection rules, and then lastly, the sample size. And then once we've done that, we're going to come down here and click Simulate. So on this first tab, which kind of sets up the overall structure of this trial, we specify that we're going to have these 2 stages, the one before the selection and the one after. And we've got the 2 groups, the HR negative subgroup and the whole population, the remainder. And here's where we tell ADDPLAN that we want to use the flexible combination test and use the inverse normal method to combine the p-values. An alternate option would be to just keep the 2 stages separate phase 2 and phase 3, in which case the final analysis would only use the phase 3 population. And here we can tell it which intersection test to use for the controlling the overall family-wise error rate. And then next, we're going to look at the next tab, the sequential design tab. In this initial design, there won't be any group sequential elements, so we simply select no interim stops. For the parameters, here we set up what we wish to simulate. So it reminds us we've got 2 analysis sets. We say any set is going to be effective if it's greater than 0. So in other words, wherever we simulate an effect size of greater than 0, that's an alternate, and we want to know the power. And then we have to set 2 things. One is the relative prevalences of the 2 groups, the subgroup and the remainder. And of course, as we set the prevalence of the subgroup, the amount in the remainder adjusts automatically. And we're going to set it to 54% in the subgroup with a remainder of 46%. And then we want to specify what effect sizes we wish to simulate. And we say we're going to look at effect sizes from 0 to 0.3. These are relative to the control rate, which is 0.34. And we're going to do it in steps of 0.05. So that's going to look at 7 different values of the effect rate in the subgroup. For the remainder, we're going to look at a smaller range from 0 to 0.2, and we're going to go up in a larger step size of 0.1. and that be relative to its control PCR rate of 0.23. So that'll create 3 different values to simulate at, giving us in total an overall number of 21 different scenarios as we do the full combination of each value in the 2 groups. In the selection, this is where we tell our plan what selection rules we want to apply to the groups. I'm going to select the rule that says we want to select any set that, compared to the best set, doesn't differ from it, it's not worse than it by more than some delta, which is here, we're going to use 0.1. And we unselect all the other options. If we selected the other options, those would be presented as different alternate designs to simulate. The effect measure here we're talking about is the simple estimate of the treatment difference, not the test statistic. And we're not doing any early stopping here, so this rule, the selection of this rule, is unnecessary. And we say we're just going to select analysis sets unconditionally. We're not going to set some required effect size threshold for them that they need to also pass. And then lastly, we set the sample size. As we said in the setup, the overall sample size is going to be 300 patients, 150 in each group. The allocation is going to be 1-to-1 between the treatment and control. And at this point, we're not going to do any sample size reallocation, so the rest of this tab is ignored. And at that point, we're set up and we're ready to run some simulations. So here's our plan, and I'll just show you how easy it is to set this up. Our plan divides itself into plans or designs, simulations, and analysis. Because this kind of design the sample size can't be calculated, it can only be derived we can only explore it through simulation. It doesn't appear on the plan tab, but on the simulation design tab, we can start looking at the enrichment design. And here we're looking at an enrichment design using rates. So we'll select that. And then over here, you can see the tabs that we've just seen on the slides. And in this big panel in the middle, you'll get to see where the simulation results appear. So we said there were going to be 2 stages, 2 groups. If the overall alpha is 0.025, we're going to use the flexible combination test with the inverse normal method and a Bonferroni adjustment. When we come to run the simulations, we'll do 10,000, and we'll move on to the next tab. Here we specify the sequential design, and here at this point it's quite simple. We're not doing any interim stopping, so everything disappears. We look at the parameters for simulation. Here we've got the 2 groups. Here we specify that the S1 had a prevalence of 54, and you can see that's automatically adjusted the remainder to be the complement of that, the 46%. The control rate was 0.34 for the subgroup and 0.23 for the remainder. For the remainder, we're going to take the default values of looking at a treatment effect from 0 to 0.2 in steps of 0.1. For the subgroup, we're going to look at a larger range from 0 to 0.3 in steps of 0.05. And we'll take the free combination of all that, resulting in these 21 scenarios. The selection rule, as we said, we're going to base it on the effect size compared to the effect size with the best effect, and we'll take any group that's within 0.1. We use the treatment difference and select unconditionally. And then lastly, the sample size. Here we have to adjust it to 150 in each stage, do a 1-to-1 allocation, and no sample size recalculation or no sample size adjustment. And then now we're ready to simulate, and it's going to simulate the 21 different scenarios we've specified. It tells us what the setup is in each of these simulations. Here they're all the same, but if we selected other options, or we could change options and go back and add further simulations, which would be added on at the bottom. And then we use this part of the table here to tell the difference. And then we can look at things like the simulated rates. And here we can start to look at the power, the probability of rejecting at least one group, the probability of rejecting the null hypothesis in the effective groups, probability of rejecting an ineffective group, probability of rejecting the full group, and the probability of rejecting the subgroup. So here you can see that summary of the treatment effects that are being simulated, and here's that section of the power to reject the null hypothesis. And you can see that in scenarios 16 to 18 here, we've got a power to reject at least one null if the effect size in treatment S1 is over 0.25. It's these here where the base is 0.23 plus 0.25. We've got a power of over 85%. And there's 90% or better if there's also some effect in the overall group, the 17 to 18 simulations. Notice that the power to reject the full population, to reject F, is lower in the last three scenarios compared to the ones above, because the treatment effect we're simulating in the subgroup is now 0.3, so it's higher, and what's happening is that the treatment effect in the remainder, it's getting harder to see that it's within 0.1 of it, because the treatment effect in S1 is now so much higher. And here you can see that looking at the probability of selecting the full group to go through to stage 2. The probability of selecting it in 16 to 18 is from 0.45 to 0.87. The probability of selecting it in scenarios 19 to 21 is from 0.29 to 0.78. And we can look at probably this a little bit easier by looking at the graphs that ADDPLAN provides. And ADDPLAN has this nice, very general graphing tool where we can select what's going on the y-axis, what's on the x-axis, and what will create different page graphs by putting in the values of interest here from the list on the right-hand side. So if we click on display, here it's already going to the display we want, but here we can see how we set it up. So we've pulled over the probability of rejecting at least one hypothesis, that's the overall power, the probability of rejecting the null hypothesis in the full population, and the probability of rejecting the null hypothesis in the S1 subgroup. And what we're going to plot along the x-axis is simply the effects we're simulating in the subgroup, and then we'll page the graphs by the response we're simulating in the other subset, the remainder. So here we've got the effect size in the subgroup varying between 0 and 0.3. We have the overall power, the blue line, the power to reject the null hypothesis in S1, which is the red line, and you can see that comfortably rising as the effect size increases, and we reach a power of about 80% if the effect size is between 0.22 and 0.24, rising to a power of about of 90% if the effect size is about 0.27. And our probability of rejecting the null in the full population here is, as you can see, is quite low. And here it's where we're actually simulating no effect in the remainder. So all the effect that's been seen is only in the subgroup. If we go to the next graph, we're now simulating a 0.1 treatment effect in the remainder, and our probability of rejecting the overall null hypothesis is now quite a bit higher, but it's still not that powerful. It's at its best, it's between 50 and 60%. And if we look at the last page, you can see that now our probability of rejecting the null in the full population rises to about 0.2, rises to 80% when both in the subgroup and in the remainder, we're simulating a response of about 0.2. As the response in the subgroup goes up, we see this effect where that means we start to run into a small probability that at the selection stage, the subgroup now looks so much better than the remainder that we don't include the remainder, and the power to detect the null, the overall null, fades a little bit, whereas the power of selecting something, in this case S1, of course continues to rise. Now, when we originally sized the trial, we were looking for a power of 90%, and so we might consider this 80% power when the treatment effect is 0.2 in both the subgroup and the remainder as a little bit disappointing, and we might say, okay, let's see if we can find a way to improve that. And one of the ways that ADDPLAN allows us to attempt this is through a sample size reassessment. And what that means is that at our interim between stage 1 and stage 2, so after we've recruited and analysed our 150 subjects, we're going to take a look at the effect size and see if, well, maybe we can require a power of the overall trial and allow the design to increase its overall sample size in order to better achieve that power if it looks possible. So that's what we're going to do for design 2. And for this, we keep everything else the same, but we go to the sample size tab, and instead of saying no sample size calculation, we're going to now enable sample size calculation, and we're going to use conditional power. So the power is going to be dependent on the treatment effect that we've observed in the first stage. We're going to say that the maximum reduction is a factor of 1, so no reduction at all, so we won't allow it to shrink the sample size for the second stage below 150. And we're going to allow it to increase the sample size in the second stage by up to a factor of 3, so to go from 150 to 450 subjects. And what we want it to do is to do a power calculation and set that new size so that we now have a power of 90% to when we complete the study. So we clear those simulation results. We go into the sample size tab. We say, do a sample size recalculation. Don't allow a reduction. Allow a maximum increase of a factor of 3, and condition for a power of 90%. And we can resimulate. And the scenario we're looking at actually is line 15 here. And we can see now that indeed our power to reject the null in the full population is now well over 80%. It's nearly 97.888. And if we look at the display, so this will be on the third page. And again, we can see that on the graph, that when this is the page where we're simulating a treatment effect of 0.2 in the remainder, and if we look at the treatment effect of 0.1 in the subset, sure enough, we've got a power of nearly 90%. And we also have a pretty good power, even if the S1 treatment effect is as low as 0.16. But what's the price of that? How much is our sample size going to increase? And as you can see here, we can have a version of the graph where, as well as the power curves, we look at a sample size curve. Here, this new green line. So let's take a look at adding that in. We do the variable setup, and what we can do is add a second y-axis, which is going to be our total estimated sample size. And now when we look at the chart, there indeed we have the green line, and we can go to the third page, and there is the total expected sample size. And you can see, there was something else I needed to change. I was just thinking that curve doesn't look right. There is another change that is made for this design that I failed to do. One of the, I don't know if you saw on that graph, but the maximum sample size was actually pretty high. It was over 500. And one of the problems is, of course, that even with a fairly small effect size, the sample size reassessment is trying to boost our sample size all the way up to the max to try to boost that power to 90%. And what we can do to stop it attempting to do that when things are actually not actually looking that good is to say, don't go through unconditionally when we make the selection, but require at least some sort of modest level of treatment effect. In this case, it's 0.05. When I do the simulation, and display the graph. Now my graph is looking more like the slide, and you can see that rather than 500 as I just had, we've now, even though we've allowed it to possibly triple the second stage, actually in practice we're not seeing a sample size of above expected sample size much above 420. Though of course that will be the average over a range of actual sample sizes, and that sample size occurs, maximum expected sample size occurs at a fairly low effect rate in S1, but of course a high rate in the remainder. And we can see that that maximum expected sample size is fairly constantly around just over 400 for our three different settings for the effect size in the remainder. To me, this seemed still quite high, and I wondered, so at this point we're now getting beyond the example in the user guide, and I thought, well, maybe we can still do quite well, but dial back on the maximum that we allow the sample size to increase by a factor of 3 to a factor of 2. So we can change that on that tab, and sure enough, instead of our worst case being over 400, it's now only over about 360. We have, however, got a small decrease in this power. We're not quite so close to 90 anymore. We're at about 85. So what happens if we use the other feature of ADDPLAN patient enrichment and also allow some group sequential and some early stopping? We're not going to add any additional interims. We'll use the interim we've got already. Some fairly simple stopping rules. We'll use a default O'Brien-Fleming boundary for the stopping for success and a simple stopping for futility at an alpha of 0.5. So if we close the graph, clear that lot of simulation results, go to the sequential design, we uncheck the no interims, we'll leave the O'Brien with as the default for the success stopping, and we add in the default stopping for futility with an alpha of 0.5. And there's another thing we have to make sure, which is that the stopping for success, so we only stop at success at the interim if all the selected analysis sets are successful. We won't stop if only one of them are. But the other one has also been selected. And this improves things quite considerably on the power front. You can see the expected average sample size has decreased very slightly. It's no longer about 360, it's about 350, but the power has gone up, and in fact it is now at 90% when the treatment effect in the overall, in the remainder is 0.2 and the treatment effect in S1 is 0.2, giving you an overall treatment effect of 0.2. So we can look at the three designs we have now with sample size reassessment with the up to a multiple of 3, a multiple of 2, and with group sequential. And we can look at them from the 3 pages, given the size of the treatment effect in the remainder. Here's with no treatment effect in the remainder, and there's perhaps a little bit of inflation of claiming the full population. Here is where there's a treatment effect of 0.1, and you can see that the probability of selecting the full population has gone up quite considerably compared to the other designs. There isn't this tailing off effect that we see at the higher S1 rates. And overall, this y-axis here for the expected sample size is always less than with the other designs. And then lastly, the case that we looked at in detail, where the treatment effect in the remainder is 0.2. And once again, overall sample size is smaller, but the power is higher. So showing the sort of efficiencies you can gain by looking at all the different design options available in ADDPLAN patient enrichment. I hope that was interesting and that you could see the power of the tool and its graphing to allow you to easily compare and easily generate the different design options. I do hope you've enjoyed that demonstration and that it has inspired you to learn more about trial simulation and our trial simulation software. You can find out more at www.berryconsultants.com or email us questions at info@berryconsultants.com. Thank you for watching.